Hello everyone, in this video, I'll guide you through a simple tutorial on designing and visualizing a satellite mission using freeware tools. The example case is a satellite in Sun-Synchronous Orbit pointing its antenna at a ground station and carrying an Earth-pointing sensor. We'll use SIMU-CIC and VTS software. For more information, see the video description. Let's get started. Open Scilab and the SIMU-CIC tool. In the initial window, enter the basic simulation information, author, project description, start time, and duration, in our case, 1 day. Set the computation time step to 10 seconds. Next, let's define the satellite orbit. There are 3 main ways to do this. Load an ephemeris file containing to-line element data. Enter an orbit state vector manually, or you can select orbit properties. This is the option we'll use, a simple sun-synchronous frozen orbit defined by just 3 parameters. Semi-major axis, 7,078 kilometers, corresponding to about 700 kilometers altitude. Mean solar local time of the ascending node. For SSO, this stays constant since the right ascension of the ascending node drift matches the sun's apparent motion. I'll set it to 11 hours. The parameter true argument of latitude can remain at 0 degrees. Next, at a ground station, go to the ground station list and select one from the predefined options or define your own ground station. I'll use Kiruna in Sweden. Click Add. The station appears in your list. You can add more if needed. Now, define the satellite attitude laws. Open the attitude list. First, add a geocentric law with type local orbital frame and match the satellite frame x, y, z with +s, -w, -q in the QSW coordinate system. Then click Add. Next, define a pointing law for the antenna. Create a new law named Kiruna pointing. Now select the attitude type, ground station pointing, sun-optimized. That way, one spacecraft axis will point toward Kiruna, while the others are adjusted so the solar panels face the sun as much as possible and the cold side stays turned away. Set the satellite boreside axis to +z. Then click Add. Go to the elementary conditions list and create a new condition, Kiruna visibility. Select type, ground station visibility. Then click Update. Next, set the mode sequence. For the default condition, assign the geocentric mode and confirm with Update. Next, define the condition Kiruna_visibility and select Kiruna_pointing satellite mode and confirm with Update. Now, configure the solar panel. Go to the spacecraft list, solar panel section, select Sun Optimized. This automatically maximizes solar illumination. Define the rotation axis as -y. The panel orientation is defined in the spacecraft frame by its rotation axis and to rotation angles, angle 1 around the rotation axis and angle 2 around a perpendicular axis, set angle 1 to 0 degree, and set angle to 230 degrees. Finally, define the sensor. Choose an elliptical sensor and set the angle sequence as XYZ, set angle 2 and 30. Save the project file. And finally, run the calculation. In the SIMU-CIC software, you can already visualize several important results. For example, the satellite's trajectory in the Earth-centered, Earth-fixed frame, the ground track map, satellite ground station visibility duration. All simulation results were automatically saved once the calculation was finished. The location of the result files is displayed here in the Scilab console window. The next step is to visualize the mission in the VTS software. Open the VTS software and load the files previously generated in the SIMU-CIC tool. Next, run the case in VTS. The default visualization windows will open, but many other visualization options are available, so don't hesitate to try out the various features. I hope you enjoyed this tutorial. Let me know your feedback in the comments below. If you liked the content, don't forget to like and share. Have a great day.